Okay, so the last thing we're going to talk about in this section on expectation are properties. Properties of expectation. So we're going to be calculating a lot of expectations. And expectation is one of the fundamental quantities that we deal with in probability. And so it's going to be useful to and very powerful to have some tools at our disposal for doing these calculations by observing some properties of the expectation. So the first is expectation of a function of x. So suppose we have a random variable x. So and f is a function. Okay, then the first observation is to realize that f of x is also a random variable. Okay. Y, if this is the probability space, we think of x as defining a function from the probability space into R. And then f is a function from the R into R. So this is f, but f of x is f composed with x, which we can define as y, can also just be thought of as a random variable. Okay, so y is also a random variable, and its expectation can be calculated by summing over the values of x, the possible values of x, not the possible values of y, possible values of x, and multiplying f of x, which is the value of y, times the probability that x is equal to x. Okay, so this is something that needs to be proven. And to prove this, we note that probability that y takes a particular value, well, this can be written as the union over all x values that map to y under f. And that's a disjoint set. So that can be written as a sum over all such x values of probability that x is equal to that given value. Okay, so that's the key to this, because we know by definition the way that we're supposed to calculate, or the way that the definition tells us to calculate expectation of y, is by summing over all possible values of y of the probabilities of y. But as we just observed, the probability of y can be expressed as this sum over x's of values of x that map to y under f of the distribution of the random variable x. And we can now bring these sums together and look at this as sum over y, sum over x. Okay. And now what we realize is that given this condition that f of x is equal to y, we can actually substitute f of x in for y here. But now that now this sum here, this is just a sum over all possible x. Right? Because you're saying we have all possible values of y, and then we're subsetting the x's according to which y they map to. But if we take it over all y, this just becomes the union over all x. So this is the sum over all x, f of x, probability that x is equal to x. This is also called the law of unconscious statistician, law of the unconscious statistician, because it was taken for granted for a long time that this was just something that could be done without actually proving it. In fact, it can be proven and it is a valid thing to do, but it does require a proof. Scaling rule. What the scaling rule says simply is that if we have a constant c, then the expected value of the constant times a random variable is just the constant times the expectation. So we can scale a random variable and the expectation scales accordingly. The addition rule says that if x and y are random variables, then the expectation of x plus y is equal to the expectation of x plus the expectation of y. Of course, provided that these expectations are well defined. Okay. All right, the multiplication rule for expectation says that if x and y are independent, then the expectation of x times y is equal to the expectation of x times the expectation of y. Okay. And finally, the conditioning rule. For the tower property. Says that if we let C1, C2 be a collection of exhaustive and mutually exclusive cases. And if we define the expectation of X given CI as the sum over X of the conditional probability of X given CI, then the expectation of X is equal to the sum over the cases of the probability of the case times the expectation of X given the case. So let's prove this, because this just brings us back to the law of cases, the law of total probability. So recall the law of cases. Law of cases says that the probability that X is equal to X is the sum over the cases, probability of the case, probability of the event given the case, additional probability. Therefore, we can calculate the expectation of X as sum. This is by definition, right? This is the definition of expectation. Here we can substitute in the law of cases. Law of cases. For the probability that X is equal to X. Next thing we do is we switch the order of sum. So we sum over I first instead of summing over X. This allows us to write probability of CI, and then we sum over X. X, probability that X is equal to X given CI. This is allowed here because it's well, this is a little bit of a switcheroo, but in a lot of cases you can switch the order of the sum. Not in all cases, but for the sake of this course, it's not an issue. And then by definition, this is how we defined expectation of X given CI. And we're done. Okay, so those are a few commonly used properties that we will come across often for expectations. This is the end of this section on the expectation. We're going to move next on to the concept of variance and standard deviation and covariance. And then we're going to continue to discuss specific families of distributions after that.